This lesson, we are looking at integrating different types of functions. Last lesson, what were we looking at? We were looking at integrating using something else, if you remember. Substitutions, right? And the substitution that we chose was, we called a U substitution, right? And we said, okay, let U equal to some expression, and that way we can make the expression simpler, right? And we can integrate that way. Now, I think the problem with like lots of tools in mathematics is that I gave the analogy last lesson about using quadratic formula to solve like, something you could just factorize. It's like a chainsaw to cut a piece of paper. The problem with this the idea now with different integration tools is that sometimes it's just the wrong tool, right? So like this is a special screw. It's called a torque screw, and like I was trying to fix my switch the other day, and I was trying to use my Phillips head. It didn't work, right? So straight up, like it's just the wrong tool. It doesn't work. I had to like get this new screw. It only works for this special thing. So it's just kind of annoying. In a similar way, we have specific tools for certain types of functions in the Extension 1 course. So as we're doing this, keep this in the back of your mind that there are a range of tools that work in specific situations, and this is one of them. In order to do and integrate these two functions, we're not going to use similar power rules or anything like that, right? So don't get in the trap of saying, oh yeah, there's a squared there, we can just add 1 to the power, divide by the new power, right? Because you can try it, and then remember, you can always check, and it won't end up being the same, right? What we can do, though, is we need two things, actually. Here's our first kind of screwdriver, right? cos²x, there was an identity for that. Think again. Think back to all the tools you've learned. Yeah, cos²x minus sin²x. And then the other one that you are probably more familiar with, this is our Pythagorean identity. Sin²x plus cos²x equals to 1, right? These are our two tools that we're going to use in order to figure out how to integrate these two functions. Okay, which one do I start with? I'm going to start with, actually, the interesting thing, Carl. The interesting thing is, we won't actually start with these expressions. I'm going to start with this expression here, right? Because if I start with this expression, here's your proof. cos²x. It's almost like a proof, right? cos²x minus sin²x. I can already see that there's these two expressions here, okay? Why is this useful? Well, the idea is, what I'm saying is, I want to find and rewrite these two expressions as something that I know how to integrate already. And we've already looked at integration of the normal trig functions like sine and cos, right? It doesn't matter if there's something different inside the brackets, we know how to deal with that. Something like this, though, I don't really know how to deal with, right? So I'm going to write this here. I've got cos²x equals to cos²x minus sin²x. And I'm going to try and make cos² the subject. So what can I do? I can do a bit of rearranging. Let's move that to the other side. Add sin² to both sides, sin²x to both sides. But I still kind of have this problem in the sense that, okay, well, I've still got this sin²x over here, right? Not much I can do with that. There's another identity, the one that you were talking about before. Sin²x can be written in another way. Well, it's pretty much just the arrangement of this. Right? So, okay, sorry. We take this one, and hang on, give me a second. We scratch that line. Okay, cool. Yeah, we scratch that line. All right, we come back to this. Let me rephrase. Okay, so the idea is that we have right now cos²x is equal to some expressions, cos²x and sin²x. We don't really quite want those, right? I want to rewrite my subjects either sin² or cos². Okay, so let's see what we can do. I've already given you this thing that we could substitute in potentially, which is why we're using a substitution essentially. So cos²x, right? Instead of writing sin²x, I could write 1 minus cos²x. Now, again, that initially doesn't seem like it solves the problem, but what you can do now is a bit of simplification, right? So here we can expand these brackets. And then when you have here these like terms, so to speak. Okay, and think about what the goal was. The goal was to write cos squared in another way so that I have a function I know how to integrate, right? What rearrangement is going to allow me to do that here? Well, I just want to make this guy the subject, right? Because I actually know how to integrate this kind of function, right? And I can do a bit of rearrangement and that won't change it. Can you guys see that? Yeah? So what do I need to do, Matt? What are the next steps?
Put the 1 on the other side.
Yep. And then you can divide both sides by 2. I didn't even put the 1 to the other side. Plus 1.
So it's going to be like half.
Yep. So they write this in a few different ways. I just want to make sure I write it the same way as your formula sheet. So if we divide both sides by 2, multiply by half, here's our first identity that we can use. So this is on your formula sheet, and this is one of the ways that we can actually now integrate cos²x. Why is that? Well, have a look at it, right? Instead of saying, oh, what's the integral of this? What's like the rule, so to speak? We use this substitution. We say, okay, if I'm asked to integrate cos²x, here's your example. Right. What you need to do is you first need to make this substitution that you have here. Right. You don't have to derive this every time. Okay. It can be a helpful exercise because sometimes they may vary questions. So be familiar with it. But this is on your formula sheet for you to utilize. Okay. So what I'm going to do is I'm going to rewrite cos²x in this way. So I've got half outside of 1 plus cos²x. And then think about how you can make integrations easy, right? We've got a constant here, so I'm going to pull that out. And then here's where you need to be careful because we're doing a lot of differentiation recently. So we need to go back into integration mode and remember, how do we actually integrate something like this? Angus, can you give me some suggestions?
If I have my formula sheet, I can help.
Okay. Well, let's start with this guy. We can integrate this guy, can't we? It's just the x, right? So now be careful here, right? We don't have a defined integral. So just by kind of convention, we don't use the square brackets. So this part I've got x. Who remembers the integral of cos²x? Cos²x.
The integral of
Sine.
Yeah, it's just sine. 2x. So the original function inside always stays the same, but there's an extra step I need to do in order to address this guy over here, right? So think about how you integrate. You usually put 1. Yeah, it'd be 1 on 2. Right, because you're taking the derivative of this, putting it on the denominator. We can just write that as half. What are we forgetting there? Plus c. Okay. Right, so what have I got here? I've said, okay, the integral of this, okay, I'm going to leave this half out here because really constants don't affect things. If you can ever factorize something out for integrals, go ahead and do that. Okay, and what you get left with is x plus half sine of 2x plus c. You can check this by differentiating. We should end up with the same thing that we started with, right? Back over here. Cool. Questions about that? Now, one thing I want to strongly warn against is that it's often common that students will try and memorize the actual integration. Like, they'll skip this, oh, why do you need to bother with the substitution? I would just remember that the integral of cos²x is something like this. Do we see any problems with that? Problems?
It's unlikely that you just
They're probably not going to give you this question in an exam, right? They're probably going to give you something with a few adaptions. So the substitution method is a much more effective way to do it. Because essentially, and I'll generalize this later on, but essentially what you're doing is you're taking this and you're doubling the angle when you put it into here. Okay, so we're going to generalize that later on. Can you do that for me now for integral of sine squared?